Why do some comets brighten in clean, gentle arcs while others hop upward in sudden steps? What makes a light curve terrace instead of rise? On OC3 2025, interstellar comet 3I Atlas passed roughly 30 million kilometers from Mars, where ESA's ExoMars TGO and Mars Express captured the coma from an unusual vantage. It now heads for a late October perihelion near 136.4 LU. These dates give us short, precise windows to watch for either smooth, heating-driven brightening or genuine outbursts. The baseline expectation is steady. Sunlight rises roughly as 1 Fagor R2 and, folded through volatile physics, produces gradual growth in dust gas output. Rotating jets can modulate that signal, but the envelope remains smooth. When the deep interior warms slowly, sublimation fronts creep inward and the coma responds with a predictable trend. Asymmetric outgassing adds small, repeatable wiggles rather than abrupt jumps. Steps, by contrast, hint at thresholds being crossed. A sealed pocket vents after a crust cracks. A previously shaded vent rotates into persistent sunlight and switches on. Or a small fragment detaches, briefly multiplying surface area. Each process injects mass faster than solar heating alone, creating a measurable step-like magnitude jump over minutes to hours. Laboratory and spacecraft case studies point to pressure release, structural failure, and phase transitions as plausible triggers for such bursts. 3I Atlas invites a clean test because we already have compositional and geometric anchors. JWST and IRZ SPEC reported a CO2-dominated coma inbound, with sunward-enhanced outgassing, unusual among comets at these distances. VLT spectra showed CN turning on while numerous Ni lines brightened and Phi remained undetected. Together, these point to low-temperature volatiles and evolving vents that could, under stress, produce step changes. We will keep our approach gentle and testable. First, acquire dense time series photometry at 2 or 4-minute cadence around the remaining October windows and, after conjunction, in early December. Second, bracket each run with quick color or line checks, CN and a green band, to separate dust-dominated brightening from gas-rich bursts. Third, pair morphology snapshots, star-registered and comet-registered, to catch a newborn jet, a sunward spike from dust in the orbital plane, or a fragment plume. And finally, tie everything to astrometry. If mass release is asymmetric, tiny non-gravitational residuals can echo the timing of a jump. If heating alone rules, brightness will track geometry smoothly. If cracking, jet switching, or fragmentation intervene, we will see discrete steps with matching changes in color or shape, and possibly small, time-linked residuals in the orbit fit. That is the single promise of this film. To show how a few careful hours near OC3 and around late October, repeated again when 3I Atlas reappears, can turn a jagged light curve into a physical diagnosis rather than an impression. The geometry is pinned by 2 anchors. The Mars Vantage on OC3 2025, when 3I Atlas passed, about 29 to 30 million kilometers from Mars, and ESA's ExoMars TGO and Mars Express secured imaging between OCT-17 and the late October perihelion near 1.4 AU around Octi 29 to year 30. Earth slides into solar conjunction mid-October. Practical follow-ups resume before sunrise in November as elongation improves and continue into December. These dates define when to compare smooth heating against true step-like brightening. Composition gives the context for what can change quickly. JWST spec measured a CO2-dominated coma at RHC at 3.32 AU with CO2, H2O, 8+1, and sunward-enhanced outgassing, the kind of mix that can alter oxygen line ratios and coma structure as heating rises. A CO2-rich driver can make activity respond sharply to geometry, especially if shallow layers vent efficiently once illuminated. From the ground, VLTX shooter or UVS detected CN00 by mid-August, while finding numerous NEI lines and no FEI at comparable sensitivity. Early limits on OI, C2, C3, and NH2 were also reported. The Ni without PA pattern and delayed CN onset imply low activation energy pathways and evolving vents, compatible with sudden releases when crusts fail or channels open. If vents switch on discretely, light curves should show upward steps that persist, not mere noise spikes. What steady heating should look like. The envelope follows incident power 11R2, modulated by the phase curve and slowly deepening sublimation fronts. Rotation and viewing geometry add repeatable wiggles, but not terraces. By contrast, outbursts inject mass on timescales of minutes to hours. A crack depressurizes a pocket, gas plus fine dust. An illuminated vent crosses a threshold and stays on, or a small fragment briefly multiplies area. The response is a step that holds or decays with a characteristic timescale set by particle size distribution and expansion losses. Model sketches guide which decay, quasi-exponential or power law, to test against the data. Tail geometry helps us avoid false positives. ID atlas tracks close to the ecliptic, so a thin dust sheet can project a sunward spike, anti-tail, when seen edge-on, a purely geometric effect that can change appearance rapidly without any true burst. Large grains confined to the orbital plane make a narrow sun-pointing feature, while the ion tail stays anti-solar. Near conjunction and shortly after perihelion, brief windows may favor a short, sharp spike aligned with the projected plane. Morphology must be read with this in mind. For orbit fits, current astrometry through late September shows non-gravitational residuals consistent with zero within tight errors. That baseline lets us ask whether any step-like brightening coincides with new residual patterns as activity rises. If a significant asymmetric thrust begins near perihelion, small, time-linked residuals should appear and grow with activity proxies. Bringing this together for observing, in hours, we can collect dense time series photometry to catch steps, cadence, quick color line checks, CN near 388 mm, a green band for C2 or OI, to separate dust versus gas-dominated changes, anesasami, paired morphology snapshots, star and comet registered to flag new jets, thin spikes or plumes, and IV, precise astrometry to correlate dynamics with brightness. Smooth 1/R2-like trends favor heating alone. Durable steps with matching color watch-arc morphology changes favor crust cracking, jet switching, or fragmentation. The October-November windows are enough to tell these stories apart. We weigh 3 explanations for step-like magnitude jumps and ask them to compete against hours-long datasets around OC3, 2025 near Mars, the late October perihelion, and the early December reappearance, H1, crust cracking and pressure release, true outburst. Threshold-type steps with decays favor H1, terrace-like repeats at P-rot favor H2, single sharp jumps plus a transient knot favor H3. In each case, we look for the same signature to re-emerge after perihelion under new phase angles. Thermal stresses or volatile buildup fracture a sealed layer, venting gas and fine dust on minute hour timescales. The light curve rises in a discrete step and then relaxes with a characteristic decay tied to particle sizes and expansion losses. Rosetta-era models reproduce such bursts from fractured terrains, with short rise and slower fade matching gas dust coupling. Support for this pathway at 3i Atlas is circumstantial. A CO2-dominated coma implies low-temperature volatiles near the surface that can pressurize pockets before water fully takes over. JWST Chan NIRA spec found CO2 H2O 7.6 to 8 with sunward enhanced outflow, conditions ripe for threshold behavior. A sudden step followed by a quasi-exponential or power law fade, little periodic repetition, and possible coincidence with subtle time-linked astrometric residuals if the jet is one-sided. H2, illumination-driven jet switching, seasonal/rotational gating. A pre-existing active vent crosses into sustained sunlight as geometry changes, outgassing toggles from mostly off to on, adding a persistent brightness offset. Rotating jets are well known to imprint repeatable features. When a threshold is crossed, the curve can show a step that repeats each rotation or holds for days if the sunlit state persists. JWST has imaged rotating jets sweeping like a lawn sprinkler in other comets, establishing the principle. At 3Ri Atlas, Mars-side sequences from OX Arcturus 1's period 7 and ground spectra showing CN onset by mid-August suggest evolving activity zones. Terraces recur at or harmonically with the rotation period. Color or CN flux grows in phase with the step. Morphology frames show a stable lobe or jet aligned with the new illumination. H3, small fragment shedding, area boost, brief plume. A piece splits from the nucleus, briefly multiplying the illuminated surface area and releasing dust. The light curve shows a rapid jump, followed by a decay as grains disperse. Case studies of fragmenting comets show step-like brightening, short plumes, and changing inner coma structure. A CO2-rich surface could make such shedding easier before water ice dominates bonding. VLT spectra report numerous Ni lines with Thea ion detected and CN present, an unusual mix consistent with evolving near-surface chemistry, but not alone diagnostic of fragments. A sharp step accompanied by a new inner coma knot or short-lived fan. No strict repetition at the rotation period. Possible later appearance of a faint companion condensation in deep stacks, guardrails, and confounders. The path of 3I Atlas lies close to the ecliptic, so an anti-tail, a thin dust sheet seen edge-on, can appear or sharpen quickly with geometry alone, creating apparent structure changes without any mass surge. If a step is geometric, the position angle of the spike locks to the projected orbital plane, and brightness steps in gas-sensitive bands, CN, OI, do not accompany it. Finally, early astrometry through late September shows non-gravitational residuals consistent with zero. A new pattern correlated with a photometric step would tip the scales toward a physical outburst or asymmetric thrust. What decides among them? Paired, dense, calibrated light curves with short CN green band checks, and 2 or 3 morphology frames spaced tens of minutes apart around late October, and repeat after conjunction in early December. Here is a calm, practical routine to tell steps from smooth heating, and to decide among cracking, jet switching, or fragment shedding. Begin with time series photometry at a steady cadence, 1 exposure every 2 to 4 minutes, for 2 to 3 hours. Keep the filter fixed for each run, note precise UTC, and calibrate with biased darks flats. H2, illumination-driven jet switching, predicting terraces that recur with the rotation period or persist as long as the vent remains sunlit. H3, small fragment shedding, predicting a sharp jump with a short-lived inner coma knot and no strict periodicity. The observing plan is intentionally simple. Gather dense time series photometry at 2 to 4 minute cadence for hours. Bracket with brief CN green red checks. Take a few morphology frames, star and comet registered, and, if possible, add precise astrometry. Measure step height. Add DM. Fit a decay, T, or power law, and watch whether offsets repeat with the rotation period. Guard against geometric confounders. A near-ecliptic path can create a thin sunward dust spike without any mass surge. Repeat the same tests after conjunction in early December under new phase angles. With many small datasets shared and aligned in time, the community can move beyond impressions and diagnose the physical cause of each jump. Plate solve every frame. Pick 2 or 3 unsaturated Gaia comparison stars close in color and air mass, and use small apertures, 2-3 f/HM, with a clean sky annulus to preserve sensitivity to quick changes. Build the light curve live. If a jump appears, continue the same cadence for at least 1 decay timescale. Add color or line checks without interrupting the main sequence. A short CN, 388 nm, or blue band set before and after the run, and a green-red pair to separate gas spikes from dust brightening. When a step is seen, measure its height dm and fit the post-step behavior with a simple model. Exponential decay with time, constant t, or a shallow power law. A persistent offset without decay hints at a jet that switched on. A decaying bump favors a pressure release plume or small fragment. Capture morphology as an independent check. Take a few high SN frames spaced tens of minutes apart and stack both star-registered, for context, and comet-registered to freeze the inner coma. Compare radial profiles sunward versus anti-sunward. Measure the position angle of any thin sunward spike. If the spike locks to the projected orbital plane, while gas-sensitive bands stay flat, that structure is geometric, not an outburst. If you can, add astrometry, short exposures to limit trailing, careful plate solving, and honest uncertainties. Correlate any step timing with tiny changes in orbit fit residuals. One-sided mass release can nudge the motion. 3 takeaways. 1. Heating alone produces smooth trends with small, repeatable wiggles. 2. A true outburst shows a fast rise and a modeled fade. 3. Jet switching creates a terrace that repeats with rotation or holds while illumination persists. Share your calibrated frames, light curves, and notes from late October and again in early December. A handful of quiet, well-timed hours can decide the story. We set out to understand when a comet's light curve rises smoothly with heating and when it jumps in steps. The question is timely. 3. Eye-Out Atlas offered a rare geometry on Oct 2025 near Mars and heads toward a late October perihelion with a reappearance expected in early December, giving us repeated chances to watch the curve evolve. The baseline expectation, solar power scaling roughly as 1R2, yields gentle brightening modulated by rotation and viewing angle. Step-like jumps, by contrast, point to thresholds, a crust that cracks and vents, a previously shaded vent that crosses into sustained sunlight and switches on, or a brief increase in active area if a small fragment separates. We kept the discussion anchored in facts and testable mechanisms. A CO2-dominated coma measured earlier suggests low-temperature volatiles can respond sharply as geometry changes. Ground spectra recording CN onset and unusual nickel lines without detectable iron hint at evolving near-surface chemistry. From this context, we framed 3 hypotheses. H1, cracking and pressure release, predicting a rapid rise followed by a modeled decay.